Hello all, Mahesh Subramaniam from Juniper Networks A data center product team. And next 28 minutes, the first off we are going to talk about a data center challenge, the main challenges as data center switch vendor, what are the issues and challenges we are seeing it, and how we are going to address those challenges with the existing technology. That will be around 10 to 12 minutes, I will talk about it. And the part 2, which is important one, those challenges, how we are going to address via Ultra Ethernet. Why? Because the ultra scale GPU clusters, making around 900,000 to 1 million GPU clusters, how we are going to make it possible with Ultra Ethernet technology. That's what we are going to cover in second part. That's what the agenda going to be today. Yeah. So, in my perspective, there are three main AI data center challenges what we have seen and what we have identified, which is help us to categorize this into two parts. The part 1, it help us to understand the AI workload behavior, that's one. Second, it help us to build the definition of the hardware requirement for the AI cluster and the advanced software solutions with the existing technology. Specifically in AI workload, involves a lot of memory transfer. You guys all are familiar with memory transfer here. Why the memory transfer? Because after the training, the results, aka called gradients, needs to be synchronized across all the GPU cluster. To do that, we had to do some memory transfer. To specifically, this data transfer peaks during the synchronization. I would say that it will go and occupy all the memory, all the bandwidth in the fabric. Also, once the synchronization is completed, this particular, the peak will go down, it will return back to the normal level. Again, the next training will start, and again the training results will come out, synchronization will happen, again the peaks will come out, and it will go back to the normal stage. It's kind of a cyclic process. This particular cyclic process made us to realize there is a high bandwidth traffic flow crossing across our fabric, and we call it as elephant flows. These elephant flows, most of people know here what is elephant flows, but as the data center switch vendor, we seeing this elephant flows in two different ways. The first way how we are seeing the elephant flows, it is a very few flows but huge. It is a very few flow across the fabric, it will flow, but it will with a huge, and it will occupy a lot of bandwidth in the fabric as well as the switch links. That's how we are seeing in one part. The second part, the elephant flows, is low entropy. What I mean here is in low entropy. Somebody could you please close the door? Thank you. So the second part, what we are seeing in the elephant flows, it's low entropy. What I mean is the variation in the flow is so less. Why? Because the memory transfer where it happens between the GPU, one GPU to other GPU, which is 1:1 communication, not 1:n communication, which means there will be a same source and destination IP address and port and protocol number. So since there is a low variation, and we have to handle it very carefully, otherwise we cannot pin the flow in the particular link in our switches. This is the challenge number 1. And the challenge number 2, it is in fact its advantage, it's an evolution of the NIC. The classical data center server, you guys everybody have seen, even storage data center servers or application servers will have a network interface card maximum up to 25 gig or 100 gig. Nowadays we are seeing at around 200 gig. But the GPU servers, NIC if you are seeing, the expensive GPU server NIC if you are seeing, it starts from 400 gig, 800 gig, and upcoming 1.6 terabit NIC. The network interface card itself, it has a 400 gig, 800 gig, and 1.6 terabit capacity of the NIC. Think about our switch capacity. So this network interface called evolution and revolution made us to build and define the hardware product with the high radix switches. The old 100 gig or 25 gig switches will not work for AI data center cluster what we have seen in front of the customers. So in general, all the AI infrastructure networking switch vendors started building the high radix switches. What I mean in high radix switches, I am talking about 64 into 800 gig, 128 port into 800 gig, or 64 into 1.6 terabit, which we started already working on it. That is in the hardware side. The third challenge related to the software. We build the high radix switches, but we need to solve the elephant flow problem, right? I want to connect the dots from the challenge number 1, the elephant flow with less entropy. How we are going to solve that problem, the elephant flows with low entropy, the static load balancing will not work. As I mentioned earlier, the static load balancing always look for the 5 tuple variation, and it will create the hash bucket to pin the packet, the flow into the egress link. The 5 are the source and destination IP address, source and destination port, and protocol number. That will not be enough for elephant flows. You have to have a kind of some intelligence to look at the link quality, how the link quality is there, then we can pin the packet, because there is no entropy, there is no variation in the elephant flows in the AML workload, right from the AML workload. So static load balancing became failure, so we started looking into different options. That is, one of the option is dynamic load balancing. And I will explain in the next slides or few slides back what is dynamic load balancing. Basically, it will give a rank to the link, which link is the healthy link, which link is a not healthy link. Those are the different challenges we have seen it, and we are addressing in different way with the existing technology. And now, you guys, I hope 99% I'm sure you guys know what is RDMA. But from the data center switch perspective, that whenever I'm talking about memory transfer from one GPU to other GPU, we need to use some technology, and everybody is using RDMA, remote direct memory access. In the remote direct memory access, from the only one server you guys know, you guys are good experts, but my concern is in the Ethernet. Between the GPU to GPU, the transfer needs to go via fabric. The fabric needs to be lossless fabric, because the packet drop will lead into the job completion time increase. Why? Because if packet drops happen, that job needs to do it again. It has to go to the last checkpoint, and the job needs to complete again. For example, ChatGPT, it took first version of ChatGPT, if I'm not wrong, it took 21 days. If there are a lot of packet drop in the fabric, it will took around 6 months. So we have to solve the packet drop issues in the Ethernet fabric. That was our big challenge. And without UEC, with the existing technology, when we talking about RDMA, some protocol needs to transfer this particular memory from one GPU to other GPU. When we look around that all the options, specifically in the NMU over fabric, there are two options, right? One is NMU over TCP or NMU over UDP. TCP will give extra overhead to the NIC side, so everybody has chosen NMU over UDP, which is nothing but Rocky V2, RDMA over Converged Ethernet version 2. This Rocky V2 transport protocol, when we adopted it, there are a lot of challenges also, right? Because one, as I mentioned, it has to be lossless fabric, which means we need to avoid the congestion in our Ethernet fabric between the two servers. The switches, all the fabric, spine and leaf fabric needs to be congestion free. If congestion happen, the packet drop will happen. When the packet drop will happen, there will be increased job completion time. That means you are wasting the expensive GPU server time. So how to do that? One, we are trying to avoid the congestion with a different kind of a load balancing. I will explain in the next slide. Second is control the congestion. To avoid the congestion, we again looked into inside of the Rocky V2 header, which is called as a BTH header, base transport header. And the base transport header have a two key ingredient, I would say. One is the opcode, where you will have RDMA write, RDMA verbs, where will be write, read, etc., etc. And another one is that Q pair, the destination GPU memory location. In the opcode, our main concern is, as I mentioned in the previous slide, the main challenge for us is the elephant flows, right? So 95% of our traffic coming from the GPU touches the leaf and spine. The traffic, when we do the PCAP, it is all about RDMA write verb only, which is 0x06 to 0x0b, that is elephant flows. So we took that one, we had done some kind of, I filed a patent also to how to take that elephant flows, how to do packet spraying, all those things we had done it. And second, what we had done, we are trying to avoid the congestion, but still if due to the burstiness, if the congestion happen, how to control the congestion in the Rocky V2, that means we have only two weapons to handle it. One is the PFC, another one is ECN. We need to tweak the PFC according to the training model, according to the traffic. We need to tweak the ECN between the NIC, all those things we had to do. So there are a lot of complication with the existing technology, but still we have deployed, and not only specific to my company, all the infrastructure vendors are, these products are selling like a hot cake. With the existing technology, with the Rocky V2, we are solving the problem. We are trying to solve the problem. How we are solving the problem? As I mentioned, in the congestion avoidance, we are kind of placing a lot of advanced intelligence load balancing mechanism. One example is, as I mentioned, dynamic load balancing. It will not only look for the 5 tuple variation, it will look the link health. How it will look for the link health in the switch? It will look for two metric. One is the port quality metric, port load metric, and another one is the port Q metric. So out of these two variants, port load metric and port Q metric, it will give a rank to the links. For example, 0 or 1 means worst link, unhealthy link. If 7 means a very good link, something like that, right? So when the GPU traffic, the RDMA traffic coming from the GPU to leaf, it will just not only look for the 5 tuple variation hash bucket, it will look for the link quality. If the link quality health is good, then it will pin the traffic to the particular link. And that works fine, but still there is unexpected spikes or bursty comes in the picture, then we are going to the congestion control. Since we couldn't avoid the congestion, we are going to the congestion control phase 2 mechanism. There we are using a DCQC, and this is data center quantized congestion notifications, nothing but the two weapon I said, the PFC and ECN. We have to tweak lot and make sure it's avoiding the congestion properly. For example, ECN needs to come up first, then only the PFC will come out second, something like that. We made some kind of a tweaking to the existing technology. And still we are facing a lot of problems when the cluster sizes grows, right? For example, as of today, we handle around 96,000 GPU cluster with the same RDMA Rocky V2 cluster. But 100 to 100,000 GPU cluster, we can handle it. Think about 900,000 to 1 million GPU cluster. This will not work. It's a nightmare to tweak all the Rocky V2 ECN and PFC bits. How we are going to solve the problem? How we are going to address this ultra scale GPU cluster? That's where the UEC come into the picture. So the spec is not yet out, you guys know, but already we, as a networking switch point of view, we already started thinking about what are the concepts are coming into the picture, how we are going to engage these things in our switches. So whenever the customer needs, we can definitely give the solution to the customer for the ultra scale GPU cluster. What's the time? I have, how long I have?
15 more minutes.
Good. So 12 minutes I completed this. Good. So in the UEC, of course, the famous vendor have an InfiniBand. Even though it's become a standard, InfiniBand it's a standard, but only very, very few vendor. I would say one vendor is using InfiniBand, and it's a proprietary kind of a thing. And second, and there again, I have two concepts here. One is the congestion avoidance and congestion control. In the congestion avoidance, they have a central control called subnet manager. Whenever the GPU wants to communicate with other GPU, the memory transfer, that time it will look for the particular clear channel, and it has the credit request and credit grant mechanism, and after that it will push that particular flow from one place to other place. That's InfiniBand. And the second, the existing technology what I'm talking about so far. All the AI infrastructure data center vendor, they will handle these two things, nothing else. I can confidently say that. One, they will have some kind of a advancing load balancing mechanism, and since everybody using Rocky V2 in the Ethernet, they will go with the DC QCN. You will hear the two words, PFC, ECN tweaking, nothing else. Around that, there will be a lot of stories and blogs and etc., but the fundamental thing is that advanced load balancing mechanism and DC QCN. These are the things which we are handling. Even our vendor, our side, my company and all the companies are handling this one. But as I mentioned, if it is ultra scale, then we have to do something else. This will not scalable. I mean, 100,000, 200,000 is okay, but more than that, this cannot be scalable. That's the reason we are going into Ultra Ethernet. And Ultra Ethernet, first we need to handle the out of order packet, because whenever we are using a flow in the load balancing flow path pinning, the flow will solve the, always flow will go and reach to the destination with in order, not out of order, in order, everything is good. But flow always stick with only one link. We don't know the link health is good or bad. Over the period, the link health will degrade, that we cannot solve the problem. But in the packet spraying, packet by packet, you are putting the link, pinning the link in packet by packet. That means you are utilizing all the switch expensive link properly. You are using all the links properly, but when it reaches to the destination, it will not be in order, it will be out of order. Due to the in between in the fabric, there will be congestion, it will reach as out of order. So we need to solve the out of order packet, which we couldn't do it in the existing technology. That's the reason UEC is good for solving the out of order packet. Of course, the second main reason is that packet spraying multipathing. That's what I explained just now, right? So those are the two key reasons for the data center switch we are looking into that, right? And also how we are solving that rigid configuration, lot of Rocky V to DC QCN configuration, how to simplify it. That another reason, third reason I would say is we are going for UEC. This is how we are trying to solve the problem in a high level, right? So now, even though spec 1 is, we are waiting for the spec version 1 from UEC, we already started looking into working groups where the switch vendor can involve and look at which concept we can take it back in our company in R&D department to build the good switch for UEC compliant switches. That's what I'm talking about. Any questions so far, by the way? Okay. So this morning also Jay Metz talked about a lot of working groups, starting from the physical storage management and link transport software working group. Out of all the working group, as of today, I and my team started looking into 3 working groups. One is the link layer working group, second is the transport working group. Software layer working group we are start looking at now, but we are mainly concentrating this link layer and transport working group. Why? Because these 2 layers are communicating with the layer 2 and layer 3. And specifically transport working layer 4 is the key difference in the UEC format itself. So there are a lot of concepts, lot of specification are getting derived in these 2 working groups. And for example, link layer retry, if any traffic loss, how you are going to send the traffic back and one more time, not from the destination directly, you have to go all the way back to the destination NIC to send again one more time the packet back to the receiver? No, it cannot possible. So we are using some kind of a link layer retry mechanism between the switches, and the switch will hold the particular packet in a temporary buffer. We can say replay buffer, it's called technically. It will hold that particular packet, if any, with a particular sequence number. If the particular packet got dropped, it will activate the particular sequence number, it will send it back in the switch itself. No need to go back to the sender. That's one of the things I can explain. Like that, a lot of features are there. And out of this, all the working group, we look at the UEC overall architecture from a data center switch perspective. All the greens no changes for us. That means if right now today, if you have a UEC compliant NIC that packet is going in, it can pass through, because the change, the real mandatory change coming in transport layer. So switch can go up to network layer without any problem, and it can pass through the UET also. So we don't have any issues to pass through the UEC packet in our existing switch. But each and every layer, you can see that there are some UEC optional features the spec is getting developed that will be useful to have an ultra scale GPU cluster. So for example, link, we took three different concepts, we are calling it as features. One is a link layer retry, just now I explained, and link negotiation and packet trimming. Likewise, UET, we are looking at the congestion management sublayers, which is NSCC and RCCC. Although CSIG is not out in spec 1, but spec 2 it will be out. So those are the feature, we are adopting it, and we are looking at how to develop it. That's what it is. And also the software layer, we are not touching that particular software layer. Even version 2 or version 1.2 or 1.1 from the UEC, if they are enabling the INC, in-network collective, that time we will look at our switches, can we enable the INC agent, how it can communicate to INC manager. There are a lot of different concepts, and specs are getting evolved, which we are trying to adopt in the data center switches. And one more thing I want to mention it here, all the features, optional features, even the UET transport features, I have a different summary slide, you can get to know all the features now. Most of the features are network interface card features, not switch features. One, switch has to recognize the particular headers or the bits, or the switches can pass through the particular traffic. CSIG is not going to out in version 1, but for example, CSIG will have a reflection header. The new Ethernet tag IEEE going to introduce in the CSIG, that the new Ethernet header will be imposed, encapsulated in the NIC side. When it reaches to the switch, if switch can understand what is that particular CSIG header, then it can go for a lot of calculation, what is the hop count, what is the round trip delay, everything it can calculate, it can impose the results into the particular header. If the switch couldn't understand, it can work as opaque. I mean, it will look at, it will not do anything, it will pass through. So that's what UEC, most of the features that we'll call it as UEC optional. If you have it, if you don't have it, you will not have any breakage here. But UET features, 2 or 3 features we need to implement, we need to develop the code in the data center switches to recognize those concepts. And for example, in the UET, earlier in the Rocky V2 transport format, that our existing technology, as I mentioned, the BTH header will have a 2 ingredient, the opcode and the destination queue pair. Always the switch will go into the BTH header using our user defined filter, and it will understand what it is and it will take the decision. But if switch can understand the UET, the BTH header will not be there, because the transport itself totally different. Still it is a RMA, remote direct memory access, but it's not using a Rocky V2 as a transport, it is using a UET as a transport, that 5 minutes, thank you. So what is the difference between the queue pair and the destination queue pair and opcode? The PDS and SES, the packet delivery sublayer, semantic sublayer, right? These are the 2 difference. So our switch needs to understand, so we need to develop the code for it to recognize the UET transport and pass through that, or take a decision to move towards the destination GPU, to move the memory from one GPU to other GPU. That's what it is. So I talked about many different ways and different thing, but this is the summary. The specification 1, UEC specification 1 will come up with all these concepts. All specifications are for us, it's a feature. So do we need to develop the feature or not? First, second column I mentioned, do need the network data center switch needs support or not, and even the NIC support or not. If you look at the NIC side, Most of the feature needs to support in the NIC side. Only 2 feature it's related to switch. One, the link layer retry. Second is the CBSC, the credit based flow control. Remaining all our NIC side implementation, we have to do it. In the switch side, what we have to do, one, we need to understand what it is. Second, we need to have an end-to-end validation. So these are the 2 things as a network vendor, switch vendor, we have to do it, and we have to build this one and coming to the market. That's what it is. Any question on this one? No, INC, it's in the software layer. Yeah, because interpreted, but there is it's in network collectives, which means that the training model will communicate it to the lib fabric, and the lib fabric will understand what kind of a collective it is, and it will share that in network collective information to the switch. That all are happening in the 5th and 6th layer, not in 4th layer. The in-network collective always happen in the software layer, not in other layers, right? And also that in-network collective, there are a lot of discussion happening. For example, it's not in the 2 things, in network collective and CSIC, it's not coming out in the specification 1, because there are a lot of discussion happening how to handle it. And basically, I know I'm elaborating, but it will be useful for you. The in-network collective basically what it do, it want to reduce the data copies, which means it want to reduce the data movement from one GPU to other GPU. Basically what it will do, it will collect all the queue pair or the memory location collective information in the switch. Earlier it was always happening in the GPU and the NIC. It will collect in the switch with a specific ASICs, and it will do the kind of a multicast, like it will given to all the people. So it will reducing the data copies and data movement in the fabric. In a way, you are saving the bandwidth, and in a way, you are reducing the job completion time. That's what it is. And but to answer your question sharply, it's happening in the software layer. Yeah. And these are the 2 things, INC and CSIC. It's not coming on specification 1. It will be out maybe specification 2 or something like that, but that's what it is. So I think the time is over, but I can summarize one very easy way, one thing. Data center switch vendors are ready if UEC specifications are ready, point 1, because we can pass through. Second, the NIC needs to support all the UEC features, all the features you have seen, right? Out of 8, only 2 are related to the switch development code base. All are remain to NIC side development we had to do. For example, Pollara 400 from AMD, they are UEC compliant NIC. So once their NIC is ready, we can take it out and we can validate it. So that is my 3rd point. So the data center switch, data center switch, what they need to do, we have to ready for the NIC development. Once they're ready, we have to put it in our, we need to validate. All the bits and pieces we need to validate it. Once that's there, we can ready for the ultra scale GPU cluster with the data center switches. That's what it is. Thank you. Yeah.